Welcome back to Math 103 College Algebra. Tonight we're going to be looking at complex numbers. In the past, in this series, we've talked about factoring quadratics. And so I have a few problems here that I want to try to factor the quadratic in ways that we've done before, and that should make sense, I hope. So if I have x squared plus 11x plus 24, remember that in order to factor that quadratic, because my leading coefficient is 1 and I just have a 1x squared, my polynomial, my trinomial, is going to be the product of two binomials, each start with x, because if I were to distribute, x times x would give me the x squared. The next thing you'll recall is that we're going to look for the factors of 24 that add up to 11. They are 8 and 3. So I'm going to write plus 3, x, whoops, don't need the extra x there. And we have x plus 8. Whether you write x plus 3, x plus 8, x plus 8, x plus 3 doesn't matter. I'm going to make my 3 look a little bit more like a 3. Then, if you recall, since x plus 3 times x plus 8 equals 0, either the x plus 3 equals 0 or the x plus 8 equals 0, subtracting 3 from both sides here, x equals negative 3. Subtracting 8 from both sides here gives us x equals negative 8. So my two solutions are either x equals negative 3 or x equals negative 8. Number 2, I have a couple of options on how I can solve that if I'd like. I could, again, factor it as a quadratic. Again, I just have 1x squared, so it's going to be x and x. But now, this is the same as x squared plus 0x minus 4 equals 0. So I want factors of negative 4 that add up to 0. And that would be a positive 2 and a negative 2. Therefore, x is negative 2 or positive 2. Another way that I could tackle number 2, and I think I've shown this in previous videos, but in this case, this is the only time with a quadratic that you'll want to do this. I could add the 4 to both sides, and so x squared equals 4. Taking the square root of both sides, x can equal the positive or negative square root of 4, which is 2. Okay. Now, if I go to number 3, if I try to factor the same way, and I have my quadratic trinomial, and I make that two binomials, x plus or minus something, x plus or minus something else, I'm going to look for the factors of negative 8 that add up to a positive 5. Now, unfortunately, there are no factors of negative 8 that will add up to a positive 5. So this is not going to factor. So let me get rid of that stuff since this is not going to factor. And I'm going to use my quadratic formula. So I would suggest using the quadratic formula in this case. So x is equal to the opposite of the b value, which is 5, plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So x equals negative 5 plus or minus the square root of 5 squared is 25. Then I have a negative 4 times 1 is negative 4 times a negative 8 is a positive 32. So this answer is messy, but I have negative 5 plus or minus the square root of 57 all over 2. Again, like I said, that's messy, but I can use a calculator, get a decimal value. I can leave it as those two exact values. We've seen quadratic trinomials that need the quadratic formula in the past. In number 4, let's try the same thing. I want to look for factors of 6 that add up to 3. The only factor pairs for 6 are 1 and 6 and 2 and 3, and neither one of those factor pairs is going to give me a sum of 3. So again, I'm going to use the quadratic formula. So x is the opposite of the b value plus or minus the square root of that b value squared minus 4 times the a value, which again is 1, times the c value, which is 6, all divided by 2a. X equals negative 3. Now, underneath the radical, you'll notice that we've got 3 squared, which is 9, minus 4 times 1 times 6 is 24, all divided by 2. So x equals -3 plus or minus the square root of -15 all over 2. Well, what's the square root of -15? The square root of -15 is a problem. Remember what a perfect square is. Like 4 is 2 squared because 2 times 2 equals 4. 9 is a perfect square. 3 times 3 is 9. In fact, even 5 is not a perfect square, but there is some number that I can multiply times itself and get 5. If I look at -15, I want to find a number I can multiply by itself and get a negative number. But we know if I look at the number line, 0 squared would be 0. Any positive number, a positive times a positive, is going to give me a positive. So any positive number squared is a positive. Any negative number, well, a negative number squared is also a positive number. There is no real number. There is no number on the real number line that I can square and get a negative number. Yet in mathematics, if something's true, it's always true. So this is going to lead us into the realm of imaginary numbers and complex numbers. Suppose I have the equation x plus 1 equals 0. I'm sorry, x squared plus 1 equals 0. If I solve this one, like I did number 2 up here, I'm going to subtract the 1 from both sides, and x squared equals -1. Then I'm going to use a different color. I'm going to take the square root of both sides. And so x will equal the positive or negative square root of -1. But what is the square root of -1? The square root of -1 represents the number that I can square and get -1. But like I said before, there is no real number that you can square and get -1. But there has to be a number, but it's not real. But it exists, but it's not real. How can it exist if it's not real? So we step into the world of what we call imaginary numbers. What is an imaginary number? The imaginary number is the number that we imagine has to exist that I can square and get -1. That number, we call it I. I is not a number. Let's be honest here. Let's be upfront. I is not a number. I is a letter. It's the first letter of the word imaginary, which is why we use I. So we say that the square root of -1 equals I, or I equals the square root of -1. Okay. If, I'm doing a lot of writing here, if I is the square root of -1, if I square both sides, what that means is that I squared is equal to -1. I is equal to the square root of -1. Okay, so I want to know that. I'm going to use that, and that's going to help us with things like, what if I get the square root of -15? What if I have the square root of -4, -6, or something? Now, I want to take a moment and interrupt myself here and say, if you recall, if I have something like the square root of 4, that equals 2. But what if I have the square root of 12? I can break 12 into 4 times 3. My rules of exponents are going to let me split that into the square root of 4 times the square root of 3, and the square root of 4 is 2. So we're going to call that 2 root 3. So what if I have the square root of -4? I'm going to split that into the square root of -1 times the square root of 4. The square root of 4 is 2. The square root of -1 is I. So the square root of -4 is equal to 2i. If, like in number 4 above, I have the square root of -15, I split that into the square root of -1 times the square root of 15. The square root of -1, we just said, is I, and the square root of 15 is an ugly number, so we leave it. And so the square root of negative 15 is I times the square root of 15. So we step into this world of what we call imaginary numbers. Okay. Now, before we go any farther, I'm going to also introduce the world of complex numbers. And I think that this makes the most sense in a couple of ways. And I'm going to try to explain this here in my limited space that I've given myself on my note guide. If I were to imagine that inside this rectangle are all of the real numbers, inside this circle over here is all of the imaginary numbers. So a real numbers like 6 or 7 or the square root of 3, 7 halves. Those are all real numbers. The imaginary numbers are like I, 2I, 3I. You can see where this is going. I root 6. Those are all imaginary numbers. But what if I have a number like 2 plus 3I? You'll notice that the number 2 plus 3I has two parts. The 2 is a real part. The 3I is an imaginary part. So I draw a bigger glob around this just to show that there's space outside the real numbers and outside the imaginary numbers, but this is really boundless. So this blob outside is really boundless. This is the world of complex numbers. Okay. I'm going to use several different colors here. A complex number is a number that can be written as a plus bi. A plus bi. What an imaginary number is, imaginary numbers are a plus bi, where a is 0 and b is not. 2i, 3i, 6i, those are imaginary numbers. So 2i is imaginary, I root 2 is imaginary, 6i, those numbers are all imaginary. A real number is a plus bi, where b equals 0. Okay, so 6 plus 0i is just 6. The square root of 3 plus 0i, the square root of 3 plus 0i is just the square root of 3. That would be a real number. Okay. 0, by the way, could arguably fit either group. 0, though, we classify that one as a real number. So now I want to look at working with what if I have a negative under the radical? How do I handle the square root of negative 3, the square root of negative 16, the square root of 50? How do I handle these things? Okay. So, like I've mentioned already above, I can split the square root of negative 3 into the square root of negative 1 times the square root of 3. The square root of negative 1 is I, and the square root of 3 is ugly, so we just leave it. So I can pull that square root of negative 1 out front as an I. Now in number 6, we can split negative 16. We can divide negative 16 or factor negative 16 into the square root of negative 1 times the square root of 16. The square root of 16 is 4. The square root of negative 1 is I. You'll notice, by the way, when I write 4i, that I put the 4 first and the I second. This is the correct way to write it. In number 5, where I have the square root of 3, arguably, it is best to write that as the square root of 3i. So the number, the value, the root 3 comes first, the I comes second. But the problem with that is, if you write sloppy, especially like I do, this tail on this radical, does it include the I? Does it not include the I? And there can be some ambiguity there. The way that we keep things clear is we put the I in front of the radical. So when there's a radical, we put the I in front of the radical. We like the radical to be last. If there's just a number like number 6, we put the I after the number. Okay. Now number 7 is the square root of negative 1 times the square root of 50. The square root of negative 1 is I, and we have the square root of 50. But don't forget that the square root of 50 can also be factored, where one of the factors is a perfect square. So before doing this step, What I like to do is say, okay, I've got my square root of negative 1, but 50 can be factored into 50 can be factored into 25 times 2. So the square root of 50 is equal to the square root of 25 times the square root of 2. The square root of 25 is 5. The square root of negative 1 is I. And the square root of 2 is ugly, so we just leave it 5I root 2. Okay. 8 has a little bit more complexity to it. So I have 2 plus or minus the square root of 24. The square root of 24 has negative 1, 4, and 6. I have the square root of negative 24, so I can factor that out as the square root of negative 1. Then 24, 4 times 6 is 24, so I can factor the 24 into 4 and 6. So I have the square root of 4 times the square root of 6, and this is all being divided by the 2. So I have 2 plus or minus, the square root of 4 is 2, the square root of negative 1 is I, and the square root of 6 stays. Notice everything is being divided by 2. This is still the result of a quadratic formula. I can go a step farther. 2 divided by 2 is 1. 2I divided by 2 is I. So 2I root 6 divided by 2 is just I root 6. Okay. Now, number 9 and number 10 lead to what could be a controversy, could be an argument. It's something we can get into. We're not going to. What I'm tempted to do, I really shouldn't tell you what you shouldn't do, but I'm going to tell you what to not do. You cannot just simplify the square root of negative 5 times the square root of negative 5 by putting the negative 5 times negative 5 under the radical and getting the square root of positive 25. That is wrong. That's a no-no. You need to simplify first. The square root of negative 5 is I root 5. The square root of negative 5 is I root 5. So now I have I times I, which is I squared, times the square root of 5 times the square root of 5, which is the square root of 5 squared. The square root of 5 squared is 5, and I squared is negative 1. So I just get negative 5. In number 10, again, I cannot simply make this one radical with a negative 2 times a negative 8 underneath. I'm going to have a problem if I do that. I would handle this one a little bit differently if I'm looking ahead. The square root of 2 is I root 2, and the square root of 8 is I root 8. I do know that I times I is I squared, which is a negative 1. I don't need the 1, I just need the negative. Then I have the square root of 2 times the square root of 8, which is the square root of 16. And the square root of 16 is 4. So this is just negative 4. So you are going to want to work on reducing the radicals. Okay. Next thing, I realize I'm going quickly. I don't want this video to take forever. Feel free always to stop, do some practice problems, come back. But come back. Adding and subtracting complex numbers is not difficult. Okay, to add and subtract complex numbers, notice that we have the real part 2 and the imaginary part 5i. 3 is the real part, 7i is the imaginary part. To add complex numbers, you're simply going to add the real parts. 2 plus 3 is 5. And you're going to add the imaginary parts. 5i plus 7i is 12i. And that is literally all there is to it. Three minus 4, right? 3 plus negative 4 is negative 1. The imaginary part's negative 2i plus 8i is 6i. It's combining like terms. So if I'm subtracting complex numbers, it's the same thing. I just have 2 minus 6 is negative 4. I'm not sure I need that plus sign. Let's get it out of the way. And then the imaginary parts of 7 minus negative 4 is 11i. We're done. Another example. Negative 5 minus 7 is negative 12. I minus negative 2i is I plus 2i, which is 3i. Adding complex numbers should seem a little scary, perhaps, because I've not done complex numbers before. What do? Add the real parts, add the imaginary parts, and it's just like combining like terms. So if I can add complex numbers and subtract complex numbers, I should be able to multiply complex numbers. You expand. Okay. 2 times 3 is 6. 2 times 7i is 14i. 5i times 3 is 15i. 5i times 7i is 35i squared. Now, this is where this gets a little bit different from factoring or expanding in the past. Remember that I squared is negative 1. So 35i squared is equal to negative 35. So I have 6 minus 35 is a negative 29. 14i plus 15i is 29i. And those are multiplied. Okay. Number 16. 3 times negative 4 is negative 12. 3 times 8i is 24i. Negative 2i times negative 4 is a positive 8i. Negative 2i times a positive 8i is a negative 16i squared. But remember that negative 16i squared, negative 16 is negative 16, but the I squared is a negative 1. So that actually equals 16. So this is a positive 16. So negative 12 and a positive 16 is 4. 24i and 8i is 32i. I should have said this adding and subtracting. I would encourage you to maybe pause the video, try number 17 and 18. And when you're done with that, restart the video and see if you got the same thing that I got. So if I look at number 17, I have 2 plus 7i squared. Don't forget that that's 2 plus 7i times 2 plus 7i. 2 times 2 is 4 plus 14i plus 14i plus 49i squared. I'm going to make this other I look more like an I than a curl. Okay. So 49i squared is a negative 49. 4 minus 49 is negative 45. 14i plus 14i is 28i. One more example. Negative 5 times 7 is negative 35. Negative 5 times negative 2i is a positive 10i. Positive 7i. And then a negative 2i squared. But remember that negative 2i squared is a positive 2. So I have a negative 35 plus 2 is negative 33. 10i and 7i is 17i. And there's how you would multiply complex numbers. So the last thing I want to look at in this video is how to divide complex numbers. It's impossible. It is not possible to divide complex numbers, so let's talk about how to divide complex numbers. How can I divide complex numbers if it's impossible to do? Well, you'll remember, let me do some little note over here. Let me go up here now, where I should put it. Let's go down here and do a little noting. Remember x plus 2 times x minus 2? X times x is x squared minus 2x plus 2x minus 4. And those cancel, and you just get the x squared minus 4. Because these two, x plus 2 and x minus 2, those are conjugates. Those two middle terms are going to cancel out. Okay, let me get this out of the way. We're going to use that principle. So what we're going to do, I'm going to make this a little bit larger, easier for me to write. So what we're going to do here is we're going to multiply the top and bottom of this fraction by 3 minus I. Okay. And we're going to expand just like normal, just like we're used to. 2 times 3 is 6 minus 2I plus 15I minus 5I squared. I'm going to stick with the numerator. That numerator is going to become, because remember, the negative 5I squared is positive 5. So the 6 plus 5 is 11. 2I plus 15I is 13I. 3 times 3 is 9, minus 3I plus 3I. Then I times negative I is a negative I squared. Well, notice negative 3I plus 3I, those are going to cancel. I squared is negative 1. So a negative I squared is a positive 1. 9 plus 1 is 10. We have not done any division yet. What we've done is we've simply multiplied top and bottom by what we call the conjugate. Instead of having a denominator of 3 plus I, we multiplied top and bottom by 3 minus I so that those middle two terms cancel. And we've changed the denominator from being a complex number to being a real number. Now we can divide. 11 divided by 10 is 11 tenths. 13 divided by 10 is 13 tenths I. Now, if you're in my course watching this video, you'll be reminded, like I said above, that a complex number is a plus bi. Your answer should be in that format. This is not a complex number. It needs to be a plus bi format. I, in my courses, am very fussy about that. If you're doing this for your own, it's up to you. If you're doing it for another instructor, I would say defer to what they say. But I am very fussy that a complex number has to be written in a plus bi form. So I would expect this. Okay, so one more. Number 20, I'm going to multiply it. And again, if you want to pause the video, try it on your own, and then come back and see if I did the same thing that you did. What I would do for 20 is my current denominator is 2 minus 3i. So I'm going to multiply the top and the bottom both by 2 plus 3i. 4 times 2 is 8. 4 times 3i is 12i. Negative 7i times 2 is negative 14i. And negative 7i times 3i is negative 21i squared. I squared is negative 1. So negative 21i squared is a positive 21. I'm going to finish my numerator first. 8 plus 21 is 29. 12i minus 14i is a negative 2i. Let's go back and take care of the denominator. 2 times 2 is 4. 2 times a positive 3i is a positive 6i. Negative 3i times 2 is a negative 6i. Negative 3i times 3i is a negative 9i squared. Again, notice that the 6i minus 6i, those cancel. You set it up that way. You designed it that way. That should happen. Negative 9i squared is a positive 9. 4 plus 9 is 13. Now, again, with these, you often will get fractions unless the problem is set up in such a way that you won't. But they happen a lot. And again, if I'm going to write this correctly in a plus bi form, my a is 29 thirteenths. My b is 2 thirteenths. So I have 29 thirteenths minus 2 thirteenths I. Okay. Now you may have been noticing this statement right here, complex numbers on the TI-84. So let's look at this then with the graphing calculator. Okay, so if I want to add complex numbers, the first thing I suggest that you do with the graphing calculator is you go to mode. If you go down to mode, real and a plus bi, you'll notice that mine is set on a plus bi. So you want to be on a plus bi and press enter there. So you select that and do second quit to go back to your home screen. Now to add the complex numbers, you're simply going to enter it into the calculator as it shows. Parentheses, always use the parentheses. 2 plus 5i. Now to find the I, you'll notice the I is right here above the decimal point. So you can go to second decimal point to select the I, close the parenthesis, plus 3 plus 7i, close your parenthesis, press enter, and the graphing calculator will add the complex numbers 2 plus 5i and 3 plus 7i, and you get your 5 plus 12i. I'm only going to do one of each here because it should become intuitive. But if I'm going to subtract 2 plus 7i minus 6 minus 4i, parenthesis, 2 plus 7i, close the parenthesis, minus, open the next parenthesis, 6 minus 4i, and close that parenthesis. Remember, the I is the second function on the decimal. Press enter, and there's your negative 4 plus 11i. Multiplying is much the same way. Okay, so if I have 2 plus 5i times, the only difference is it's just times, so I have a multiplication. You can hit the times button or just have the two parentheses. 2 plus 5i times 3 plus 7i, close that parenthesis, press enter, and you'll notice you get your negative 29 plus 29i. Adding and subtracting, I don't know that it's worth using the graphing calculator. Multiplying, it may be. Now check out the dividing. Remember I told you it's impossible to divide complex numbers. I need to use this algorithm I showed you a few moments ago. If I want to do the division on the graphing calculator, however, parenthesis, and we're going to do the same one, that 2 plus 5i divided by 3 plus I. 2 plus 5i, close the parenthesis, divided by, open the parenthesis, 3 plus I, and close your parenthesis, press enter. Now you'll notice that the calculator gave you decimals. Again, this is going to depend on the instructor, the situation you're in, where you're using this. If the decimal's okay, you're good to go. If it's not, remember all you have to do is go to math, number 1, enter, and the calculator will put it back into fraction mode. Okay. Now speaking of fraction mode, the other thing you could do, instead of entering it the way that I did, and I'm going to go ahead and do number 20, because I could do alpha y equals, and you see number 1 there, that gives you a fraction on top and on the bottom. At this point, the parentheses would be optional because you have 4 minus 7i, go down. That's being divided by 2 minus 3i. Press enter. And notice in that form, the calculator gives you the fraction automatically first. And again, it's in the correct notation, 29 thirteenths minus 2 thirteenths I. Okay, so there's a look at complex numbers. Please remember to like the video, subscribe would be great. Tell your friends. I'll see you next time. Thank you.